Study of gas laws. Diffusion and effusion of gases. It is commonly observed that whenever two gases are placed in contact with each other, they readily intermix with each other without the aid of any external agency. Such a phenomena of intermixing of two or more gases, irrespective of density relationship and without the help of external agency, is called diffusion. And effusion is a process in which a gas escapes from high pressure region to low pressure region through a porous portion with microscopic holes or through a single pinhole. Then to explain diffusion further, the scientist Graham gave some law, that is Graham's diffusion law. According to Graham, the rate of diffusion of a gas at constant temperature and pressure is inversely proportional to square root of its molecular weight. That is, rate of diffusion of gas is inversely proportional to square root of molecular weight of a gas at constant pressure and temperature. Comparing the rate of two gases, R1 upon R2, that is equal to square root of M2 upon M1, that is at constant pressure and temperature. Since molecular weight of a gas is equals to 2 into vapor density, vapor density is represented by rho, therefore the expression becomes R1 upon R2, that is equal to square root of rho 2 upon rho 1 at constant pressure and temperature. The rate of diffusion of two gases under different pressure can be given by the following expression. R1 upon R2, that is equal to square root of M2 upon M1 at pressure P1 upon P2 at constant temperature. For the rate of diffusion, R can be expressed in the following terms as well. Rate is equal to volume diffused, capital V, upon time taken in diffusion. That is equals to moles diffused, small n, upon time taken in diffusion. It can be also expressed as rate of diffusion is equals to distance traveled in a narrow tube. That is small d upon time taken. Therefore, according to Gram's law of diffusion at constant pressure and temperature, V1 upon T1 into T2 upon V2, that is equals to square root of rho 2 upon rho 1, or square root of m2 upon m1. Here V1 and V2 are volumes diffused in time on T1 and T2. Other expression, d1 upon t1 into t2 upon d2, that is also equal to rho 2 upon rho 1, that is also equal to m2 upon m1. Here d1 and d2 are distances traveled by molecules in narrow tube in time t1 and t2. The other expression in terms of moles diffused is n1 upon t1 into t2 upon n2, that is equals to square root of rho 2 upon rho 1, that is also equal to square root of m2 upon m1. Here n1 and n2 are moles diffused in time t1 and t2. Also, we have relation for moles. N equals to W by M, that is weight upon molecular weight. So by equation, N1 upon T1 into T2 upon N1, that is equals to M2 upon M1. Substituting the value of N in this equation, W1 upon M1 T1 into M2 T2 upon W2, that is equals to square root of M2 upon M1, or W1 upon T1 into T2 upon W2, that is equals to square root of M1 upon M2. Here W1 and W2 are weights diffused in time T1 and T2. One numerical problem based on Graham's law of diffusion. 20 centimeter cube of SO2 diffuses through a porous plug in 60 seconds. What volume of O2 will diffuse under similar conditions in 30 seconds? Solution. Initial volume V1, that is 20 centimeter cube. Initial temperature T1, that is 60 second, that is for sulfur dioxide gas, and mass of SO2 gas is 64. The final volume V2 is V. The time T2 is 30 seconds, and mass of the gas, that is oxygen, is 32. Now substituting these values in the expression, V1 upon T1 into T2 upon V2, that is equals to square root of M2 upon M1, that is 20 upon 60 multiplied by 30 upon volume V, that is equals to square root of 32 upon 64. So here final volume comes 14.14 centimeter cube.